Welcome back, dear learners. This lecture is again for B.Sc first year physics students, paper number 1, semester 1. Name of the paper is Mechanics, Properties of Matter, and the unit is viscosity. In this lecture, we discuss about Bernoulli's theorem. Bernoulli's theorem is related to the flow of fluid. Related to the viscosity of the fluid. So, what is Bernoulli's theorem? What is its statement that we see? See here, Bernoulli's principle states that an increase in the speed of the fluid occurs simultaneously with a decrease in static pressure or decrease in the fluid's potential energy. Then, if we decide to prove this Bernoulli's theorem, then we have to consider a fluid of negligible viscosity moving with laminar flow as shown in figure. I will show you figure also. Here this figure. Fluid is moving through this pipe. L1, L2, these are the what lengths. V1, V2, these are the speeds. P1 pressure, A1 area of cross section, P2 pressure, A2 area this cross section. Suppose this point is one point and this is another point. At point first, pressure P1, area of cross section A1, like this. Here it is given. Let the velocity and area of the fluid column be P1, V1 and A1 at Q point. This point is suppose Q point. And P2, V2 and A2 at R point. Let the volume bounded by Q and R move to S and T. Then Qs is equal to L1 and RT is equal to L2. Yes, this volume is moved from this to this. So this one is L1 and from this to this it is what? L2. It is shown in figure. RT is L2 and Qs is L1. And this is Qs and this one is what? RT. The work done by the pressure difference per unit volume is equals to gain in kinetic energy per unit volume plus gain in potential energy per unit volume. Their sum is nothing but total work done by the pressure difference per unit volume. And this can be obtained by using this. That is A1 L1 is equal to A2 into L2. Work done is given by work is equal to force into displacement along the direction of the applied force. Then this force into displacement can be expressed in terms of pressure and volume P into V. Then net work done is given by P1 minus P2. Kinetic energy, formula half mv square. It is equal to half volume into rho v square. It is equal to half rho into V. Since V is equal to 1, kinetic energy gain is equal to half rho into V2 square minus V1 square. Then P1 plus half rho V1 square plus PGH1 is equal to P2 plus half rho V2 square plus PGH2. Therefore, P plus half PV square plus PGH is equal to constant for a horizontal tube since H1 is equal to what? H2. Therefore, P plus half rho V square is equal to constant. It means the sum of the pressure and kinetic energy remains constant. Therefore, this proves the Bernoulli's theorem. Here we can see that if there is an increase in velocity, there must be decrease in pressure and vice versa. What we conclude? Increase in velocity, there must be decrease in pressure and vice versa. In the sense decrease in velocity, there must be increase in pressure. So in this way, easily we can prove this theorem. Now let us turn Pauli's law of flow of liquid. What is Pauli's law of flow of liquid? See statement. The flow rate. I mean, what is the rate of flow of liquid? Flow rate through a narrow tube is directly proportional to the radius r. Pressure gradient delta P between the 2 points and inversely proportional to the viscosity of the fluid and length of the tube. The flow of liquid through the narrow tube depends upon the length of the tube, capital L, the radius of the tube, small r, pressure gradient delta P, and viscosity of the fluid. So rate depends upon L, small r, and delta P, and delta P as well as viscosity of the liquid fluid. So derivation of Euler's equation is Q is equal to, rate of flow of liquid is equal to delta P r raised to 4 upon 8 eta L, where r is what? Radius of the pipe or radius of the tube, eta is viscosity, and L stands for length, already we have seen. The pressure gradient delta P denotes the pressure differential between 2 points of the tube. P1 represents the high pressure in the tube and P2 represents the low pressure area in the tube, so that the liquid flow rate can be calculated by delta P, that is change in pressure, P1 minus P2. The radius of the narrow tube will change the pressure of the liquid flowing through it. Pressure of the flow of liquid depends upon the radius. Radius changes, then what happens? Pressure of the liquid also varies. The viscosity of the liquid will also change the liquid flow rate. Liquid flow rate depends upon viscosity also, not only the radius. Let the length of the narrow tube will increase or decrease. If length of the narrow tube is increased or decreased, then also there is change in what? Rate of flow of liquid. Length of the narrow tube will increase or decrease the liquid flow of the rate. Flow of liquid depends upon length of the narrow tube also. So the derivation of Euler's equation can be determined through all the above elements. In this way, the resistance R is given by 8 Ln by pi r raised to 4. So then above equation becomes the above equation of flow rate becomes Euler's law of flow rate Q is equal to delta P into what? This R. In this way, the SI unit of viscosity, one has to remember, that is dynamic viscosity is Pascal. The viscosity of the liquid is dependent on the force N per unit area in meter square divided by the rate of shear. Newton meter square per second. The coefficient of viscosity of water by Pauli's method. Pauli's investigated the steady flow of liquid through a capillary tube. He derived an expression for the volume of the liquid flow per second through the tube, so that we consider a liquid of coefficient viscosity eta flowing steadily through the horizontal capillary tube of length L and radius r. What we are considering? We are considering a coefficient of viscosity eta Length of the tube is L and radius is what? R. If pressure P is the pressure difference across the ends of the tube, then the volume V of the liquid flowing per second through the tube depends upon eta R and the pressure gradient, where K is constant of proportionality. V is directly proportional to eta R raised to X R raised to Y P by L. Then we obtain by removing this proportionality sign, where K is constant of proportionality. Rewrite the above equation in dimensional form. We obtain like this. Then if x is minus 1, y is equal to 4 and z is equal to, substitute the above values in our above equation, then we obtain v is equal to kpr raised to 4 upon eta L. Experimentally, k was found to be equal to pi by 8. Therefore, v is equal to p pi r raised to 4 upon 8 eta L. This is known as Pauli's equation. This is said to be what? Pauli's equation. Then what are the practical applications of viscosity? Importance of viscosity can be understood with the help of suitable examples which are given below here. First one is the knowledge of coefficient of viscosity of organic liquids is used to determine the molecular weights. To determine molecular weights. Second one, the knowledge of coefficient of viscosity and its variation with temperature helps to choose a suitable lubricant for specific machines. In light machinery, thin oils with low viscosity is used. In heavy machineries, high viscous oils are used. In this way, we can utilize the liquids with the different viscosities depending upon the machinery. Either it is light or it is heavy. In case of light, already I have told you, thin oils, and in case of heavy machines, very viscous oils are used. So that we have to study the concept of viscosity of the fluid. That's why we are seeing, that's why we measure the viscosity of the liquid, because viscosity again changes with change in temperature, change in pressure. That point also we have to take into consideration. Because in case of machines, whenever it is used oil, temperature of machine may go on changing. It is increasing. Sometimes it remains constant. So that we have to think and which oil is to be used for that machine. That one has to think, so that we can measure the viscosity of the liquid, and that particular viscous liquid is used for that machine. So in this way, there are various applications of viscosity, practical applications of viscosity of a fluid. So which liquid is to be suitable for a particular specific machine, that is to be obtained by using the study of viscosity. So remaining matter we shall see in next lecture. Here most of the points from viscosity chapter which are related to our syllabus of SRTMU are mostly completed here. So remaining one more chapter is left. That chapter we shall continue in next lecture. Thank you. Wish you good luck.